Hello everyone, my name is Neelanjan and welcome to this session on chaos engineering. We will talk about the whys and hows of chaos engineering to understand its requirement and also take a look at how LitmusChaos can simplify your chaos engineering requirements. We'll kick off the session by fundamentally assessing the requirement of chaos engineering in the present context and challenges it seeks to address. Then, we'll try to identify the exact requirements that can motivate one to adopt chaos engineering for any given business use case. And finally, we'll understand how the LitmusChaos framework does the heavy lifting for you to create all the different chaos engineering scenarios that can highlight the weaknesses in your applications. Before we get into the talk, I would like to briefly introduce myself. I work at Harness, the primary sponsor of the LitmusChaos framework, and priorly I worked at Chaos Native, the founder of the LitmusChaos project. In my day-to-day work, I am responsible for assessing the chaos engineering requirements for any given scenario and authoring the chaos experiments that can suitably validate the resiliency of an application for that scenario. From my experience, I can tell you that the successful chaos engineering practitioners come to master the skill of fabricating every chaos experiment on a case-by-case basis to leverage the most results out of each experimentation. In this regard, it is crucial to understand and emphasize on the right kind of experimentation with realistic hypotheses to simulate real-life failure scenarios. So with that, let's see what's chaos engineering. Let's take a detour to first understand the resilience and reliance of the digital economy on cloud computing. According to the Cloud in 2021 report by O'Reilly, cloud adoption is steadily rising across industries, with 90% of the organizations using cloud computing. This is an increase from the last year's survey, which reported that 88% of the respondents use the cloud, proving that cloud adoption is proceeding rapidly even during a global pandemic. The same report discovered that in every industry, at least 75% of the respondents work for organizations using the cloud. The most proactive industries include retail and e-commerce, finance and banking, and software. Therefore, cloud computing is potentially powering every aspect of our digital economy. However, apart from all the good reasons to choose cloud computing, we should also take into account the challenges that are plaguing it. One of the challenges is downtimes. When your network or application unexpectedly fails or crashes, IT and downtimes can have a direct impact on your bottom line and ongoing business operations. In some extreme cases, data and monetary losses from unplanned outages can even cause a company to go out of business. According to the 2021 Data Protection Survey by VM, the average downtime for an outage was 79 minutes, with the cost of downtime averaging $84,650. According to ITIC, in 2020, 1 in 4 enterprises indicated that a single hour of downtime can cost their firms from anywhere ranging from $1 million to over $5 million, exclusive of any legal fees, fines, or penalties. The impact cannot be solely measured in cost per hour. There are many other potential downsides to outages as well. According to the respondents of the survey, there are 3 core impacts of the downtime: external impact, including loss of customer confidence and damage to the brand; internal impacts such as employee morale and diversion of resources; and finally, litigation and regulations, which can have a significant effect on company valuation. The need of the hour is therefore to mitigate, if not completely eliminate, the predicament of the downtimes. What organizations need to acknowledge is that it's not a question of if, but when will their organization will be affected due to one such downtime, as evident from all the service outages headlines from 2021. While one can prepare for the apparent causes that need attention, no one can fully anticipate an overwhelming downtime before it actually takes place, and there are a plethora of ways in which things can go wrong. With the entire applications now changing their pace of hours and minutes for the much needed competitive edge, how can we ensure that our distributed systems always withstand the chaos of the adverse situation? By breaking them on purpose with chaos engineering. Chaos engineering is the way to go for all those enterprises who want to prioritize resiliency and reduce downtimes for their customers. It is about adopting a culture of building resilience against the unforeseen challenges with their systems. So how does one make a system resilient against something unanticipated? by understanding the system behavior under turbulent situations, which are representative of the real world failure scenarios. The key to successfully practicing chaos engineering is to understand the complexity involved in your system through realistic experiments and hypothesis conditions. Only by fully understanding the pros and cons of your system will you be able to choose the right kind of measures for your system. By breaking things on purpose, we come to understand the behavior of our systems in a whole new light, which is essential for defining the resiliency of our systems by measuring them on essential parameters such as fallback or how well does your failover plan work. At its core, chaos engineering is all about productively breaking things to ensure the resiliency. It's critical to ensure that the failover plan is capable of sustaining the chaos, utilizing attributes such as amount of time required to spin up a new host node if one of them shut down, so on and so forth. Second is consistency, that is how safe is your business data. The resiliency of data is vital for every business. Safeguarding the systems against data inconsistency and data loss across the hybrid cloud and or multi-cloud infrastructure is fundamentally crucial, which can be achieved through various checks such as the latency across the infrastructure services communicating with the data can be checked, so on and so forth. Lastly, price, that is how cost efficient is your failover plan. It's worth considering the capital investment required to sustain the chaos. Knowing just the right amount of resources required to survive the chaos helps predict an accurate cost profile. So this can be done by ensuring the appropriate checks such as calculation of operating costs for various failure scenarios, so on and so forth. In this regard, it is also paramount to conform to chaos engineering practices that assess your entire application against a particular failure scenario and not just a single constituent service. This means that your underlying tech stack shouldn't pose a limitation on your chaos engineering practices, and it should cover all the possible ways in which your application might fail. So let's see how you can make your Kubernetes application resilient with LitmusChaos. LitmusChaos is a tool set to do cloud native chaos engineering. It helps both developers and SREs automate the chaos engineering experiments at different stages within the DevOps pipeline, like development, during CI/CD, and in production. Fixing the weaknesses leads to increased system resiliency of the system. Litmus adopts a Kubernetes native approach to define the chaos intent in a declarative manner via CRDs or custom resources. It uses the operator pattern and relies on custom resource definitions to define the experiments. On top of that, LitmusChaos provides a UI known as the LitmusChaos Center dashboard, where one can orchestrate and visualize the results and metrics of the conducted chaos testing scenarios. It also features the Litmus API for programmatically injecting and managing the chaos, features for teaming and collaboration, GitOps management for chaos, and Chaos Hub as an open source marketplace for the experiments. It's worth mentioning that LitmusChaos has seen tremendous growth and adoption in major enterprises dealing in all kinds of technologies, further validating the need for chaos engineering and its versatile applications in all kinds of technical domains. There are more than 50 LitmusChaos experiments that can be broadly classified into two categories, such as Kubernetes and non-Kubernetes experiments, where the Kubernetes experiments can be further divided into pod level, node level, and application specific experiments. The pod level experiments inject chaos on the application level by typically depriving the application of some dependent resource such as CPU, memory, network, I/O, etc. Some of the examples include pod delete, pod DNS error, etc. Node level chaos experiments target the underlying Kubernetes deployment infrastructure. They tend to have a higher blast radius and affect more than one application deployed on the Kubernetes cluster. Some of the examples include node CPU hog, node memory hog, etc. Application specific experiments render a failure scenario pertaining to a given application deployed in a cloud native environment, such as the Cassandra pod delete experiment or Kafka broker pod failure experiment. Lastly, the non-Kubernetes experiments typically target the public cloud infrastructure resources such as the AWS, Azure, GCP, on-premises VMware infrastructure, and even bare metal servers. Non-Kubernetes chaos experiments are especially helpful for validating the entire application resiliency, even when your cloud-native services coexist with the existing critical services that are part of the traditional technology stack. For example, it includes EC2 terminate by ID experiment and Azure disk loss experiment, as well as VMware VM power off experiment, etc. It's also worth mentioning that LitmusChaos experiments also support BYOC, known as Bring Your Own Chaos, which lets you integrate any third-party tooling to perform fault injection. They can also be paired with Litmus probes to automate the process of validating the resource state before, during, and after the chaos interval. With that, we are now ready for a quick demonstration of LitmusChaos, where we'll see that how you can easily inject chaos into your Kubernetes application. Hey there, welcome everyone to the demo, but before we actually go ahead and create our chaos experiment, as you can see I'm here in my chaos center, I would like to introduce you to the boutique app. The boutique app is a classic e-commerce application, you can say, which exhibits various facets of a e-commerce application. You have your product page where you will be able to see the different products, you have your cart, you have all these components that are typically present in a e-commerce application. What's so special about this e-commerce application is that it's completely composed out of Kubernetes microservices. You have individual deployments for each of these microservices, and therefore it is constituted entirely out of Kubernetes microservices. So what we are going to do today as part of this demo is that we are going to assess the resiliency of these applications against a network loss chaos experiment. As the name of this chaos experiment suggests, we are today going to assess the resiliency of a deployment against the network loss experiment. So more specifically, what we are going to do today is that we are going to inject the network loss chaos against the cart's deployment. So the cart, as you understand, is where you will eventually add all your products that you are meaning to buy. So here's the cart that we are meaning to target. I would also like to draw your attention to the Grafana dashboard that we have. So this Grafana dashboard is made for the boutique app only. So you can see that we have our probe success percentage for the black box exporter, which is indicating that everything is normal right now. We are seeing a constant 100% probe success percentage, and the cart's QPS is also relatively stable between 40 and 60 QPS, so nothing major going on right now. So this indicates normal system behavior, but let us see that how it behaves while we are subjugating our application to chaos. So for that, I'd like to now show you how we can do that using LitmusChaos. The first step is to create a chaos workflow. So I'll try to create my chaos workflow. I'll choose self agent, then I'll go next and I'll choose chaos hubs, because in our LitmusChaos hub is where our network loss experiment is present. I'll go next. Now we can name it as let's say cart failure scenario. Go next, and then I'll add our pod network loss experiment. So this is the pod network loss, and now we would have to simply provide our values, or basically we would have to edit this experiment so as to configure it to inject the chaos within our specified resource, which is the carts. So first step is basically to add the application namespace here. It is the boutique, basically our boutique app is installed in the boutique namespace. Then we would have to choose the app kind, that is the resource that we are trying to target. So we'll be choosing deployment since it is a deployment, but you can also target stateful set, daemon set, so on. Lastly, we would have to specify the label. So here's the label, that is app is equal to cart service, that we are going to target. We'll go next, and now we can basically add a probe. Probes are a way to automate the process of hypothesis validation while you're performing chaos. It allows you to check for a particular condition while your chaos is running, and that condition is validated based on what you are defining here in the probe. So for example, I'll name this probe as, let's say, cart probe, and it will be kind of an HTTP probe, because what we are going to do here is that we are going to continuously send some GET request at an API endpoint. But which API endpoint? So as we saw earlier is that we have a cart API endpoint which we are going to target. This is basically the cart, since we are essentially deleting the cart itself. So I'll add the API endpoint here. We'll also set up a few properties, such as we'll give it a timeout of, let's say, 5 seconds, and we'll retry only once in case that we are not able to validate ourselves, and at an interval of 1 second. With that, we now have to actually define that criteria through which we are going to perform the GET request. So basically we are going to perform a GET request, and the criteria for the validation of this GET request is we are expecting a response code of 200. So response code 200 indicates that everything is correct, and right now our application API is still available. But if it is not 200, then we can be assured that something is amiss with our application deployment. So with that, we can basically add our probe and go next. Now we would have to configure the basically the envs for our experiment. So first we have the total chaos duration. We can leave it at 60 seconds. That is, for 60 seconds our chaos duration will go on. And the network packet loss percentage, that is basically what percentage of packets are getting dropped during the chaos. So we will be dropping 100%, that is, everything will be lost. Now we would have to provide our container runtime. So I happen to be running a container container runtime for my Kubernetes, so I'll just update it accordingly. Okay, so we have updated our socket path and container runtime. I'll now update the pods affected percentage. So we have only one pod effectively, but if we are giving 100 pods affected percentage, that would mean that one pod is getting affected in effect. So yeah, we can basically finish up, and that's how easy it is basically to describe your chaos scenario in a declarative fashion here in LitmusChaos. We can turn the revert schedulers off, since we would like to actually see the logs and the chaos result at the end of the experiment. So yeah, we can go next, and we can define the weight of this experiment for the calculation of the resiliency score as 10, because we have only one experiment, so therefore we can have only 10 as weight. We'll go next, and here in the chaos schedule we can schedule it right now. Go next and then finish. So yeah, our chaos scenario has successfully finished, and we can see that it has started running. So currently our chaos experiment is getting installed, that is, the pod network loss experiment is getting installed. Alright, it looks like we are just about to start with our chaos execution. So the pod network loss experiment has actually started to execute right now. So what will this experiment will first do is that it would validate the steady state conditions, that is, whether the target application pods are available or not, whether they are healthy or not, that is, whether they are running or not, and only after those conditions are met we'll be going ahead with the chaos injection. So the way we are going to measure the impact of the chaos is we are going to basically go to our Grafana dashboard and see if there is something wrong. So as you can see that over here the red annotation denotes the duration of the chaos, and there's definitely something going on because our black box exporter goes down, so that indicates that our application API endpoint is in fact not available. We can validate that if we go a refresh. You can see that it's actually unavailable, it's not coming back with a particular response. We can further see the impact here as part of our cart QPS. The QPS is going down, it's way below 40 and nearing towards 20 right now, while the access duration over here is like going up. Earlier it was in the vicinity of 3 to 4 seconds, while it's coming right above 6 to 8 seconds. So with that we have actually established that the chaos has been injected. However, although we are able to monitor the chaos here using our Grafana dashboard, The LitmusChaos will make it easier for us using the Litmus probes to automate the process of the validation of our chaos while it is happening. In other words, we want to measure the impact of the chaos in an automated fashion so that a condition that we want to be stable across the chaos can be measured. So let us see what is the probe outcome here and how it is getting reflected in the chaos result. Looks like our chaos duration has passed, and if we go back here, you can see that our experiment has also finished. So let us try to actually see the logs and result for the same. Over here we can see that we have quite a few experiment logs. These are depicting the different steps of the experiment, where we are first of all performing the steady state check, then we are basically performing the probe checks throughout in a continuous fashion, and you can also see the number of pods that are getting targeted. So we have only one pod, therefore it is getting targeted, and the name of the pod, so on and so forth. Then the chaos is running throughout the chaos duration, and finally we can see that our probe had actually failed, and that is the main reason that our experiment has failed. To get a quick glance at what happened here, we can go to the chaos result, and if we scroll down, we should be able to see that our experiment status is completed, but the verdict is failed, and the reason for that is probe success percentage is 0, and the probe in question was the card probe that we had defined, which is an HTTP probe, and it is not available right now. So in this way we saw that how we can basically set up a chaos experiment for the chaos testing of your Kubernetes application. We also defined a Litmus probe in order to automate the process of hypothesis validation in a simple and declarative manner. So